Okay, so chapter 7, section 3, like I said, is a very short section. There's not a lot to it, so I think we'll be fine here. Metallic bonding. So far we've discussed ionic bonds. We know about how ions are formed. We know about how valence electrons affect that. We talked about how the electrons are transferred to form the bond. And we know that the bonds are strong, have high melting points, high boiling points, and they conduct electricity well. So that's the ionic category. Another category of bonding is metallic bonding. And what I want you to be able to do for this section is number one, I want you to be able to describe the valence electrons in a metallic bond. And because if you can describe the valence electrons, you can understand why metallic substances have the properties that they do. And then I want you to be able to explain what an alloy is. So those are our objectives. So let's begin with the first part, metallic bonds. What are they? Well, for metallic bonds, you are going to have valence electrons. So these are the electrons that we can use in bonding, okay? But the thing about these valence electrons that is very different than ionic is these are mobile. They are able to just move any which way they want to around the nuclei. So basically, let's say we're looking at the metal copper. If this was copper down here at the bottom, all those positives would be little copper nucleuses. Okay. And then we'd have negative electrons. But instead of just being attached to one copper nucleus, it can flow all around all of the nuclei that are in this metal. And that's the only thing that exists there. So we have mobile valence electrons. It is very, very important that we recognize that our electrons have the ability to move. This is one of the things that makes metallic bonding unique, gives it its own category. These electrons are able to move so often and so well, we actually refer to this as the sea of electrons. All right, so metallic bonds have mobile valence electrons. We call it the sea of electrons because they're always in motion. And if we think about looking at a sea or an ocean, it's never still. The water's in constant movement. The same thing is true of the electrons in a metallic bond. They're constantly moving. Because of this sea of electrons, we observe some of the things that make a metal a metal. When we think of copper, or if we think of aluminum, or we think of iron, we think about types of materials that have malleability and ductility. Malleability and ductility just refer to being able to be drawn into wire, being put into sheets. It's a metal. It's something that we can hammer, we can mold, we can shape. These properties of the characteristics of the metals, the metallic bonds that we kind of are familiar with, is because of the sea of electrons. Because those electrons are not set into these very fixed, rigid structures, they're not in that crystal lattice structure, which is very, got to be here, got to be here. It's very organized and so forth. This doesn't have that. Because of that, though, then we can move these electrons somewhat out of the way when we need to. The bonds won't break when we apply pressure to them. Instead, they will just accommodate the pressure. This allows us to hammer something down or to draw it into wire. The electrons move. All right, so malleability and ductility, that's being able to be hammered into sheets or drawn into wire. We've already done that once. We're doing it again. We're talking about it. They are going to be smushed into the empty spots. And I have a real quick animation from YouTube we're going to watch that might help us see that a little better. So, like I said, just real quick.
definition of a metallic bond from our overview video? Well, let's see it in action. Here we have a bunch of copper atoms.
Oh, why is
and
this
like all
not?
metals, they have a medium
Hang on.
electronegativity. So if the situation...
My screen is showing this. I don't know why. Hold on. I'm not sure why it's not showing on yours. Maybe I have to end the show. We'll try it that way. No? Here we go. All right, well, I guess we can see it this way. All right, it's only a minute long, and then we'll finish up our note part.
This video is about metallic bonding and IB chemistry. Do you remember the definition of a metallic bond from our overview video? Well, let's see it in action. Here we have a bunch of copper atoms, and like all metals, they have a medium electronegativity. So if the situation's right, they can be persuaded to give them up. When they all get together, they decide to share all their valence electrons. These shared valence electrons are called delocalized electrons because they're free to roam around. And as you can see, the positive metal ions form a rough lattice. Here we have silver. And like all metals, the delocalized electrons of its metallic bonds are free to move around, which means that silver and all metals can conduct electricity quite well. Here we have gold, and here we have Thor. Now, gold, like all metals, will not just simply break when we hit it. Instead, the gold will deform upon impact or bend a little bit. This is because the metallic bond allows for the lattice of positive ions to shift or change shape a little bit without breaking the bonds. This is why metals are malleable. It's also why they are ductile, which means they can be drawn with wires. Sorry, Thor, maybe you should have used a cool metal name like Iron Man.
Oh,
The
so
end.
funny.
Thank you.
All right, let's go back to this. So they're malleable and ductile because their electrons are mobile. We're able to move them out of the way in order to accommodate. We don't break as soon as the pressure is applied. This also allows metals to conduct electricity very easily. It's the same concept as when we were talking about electrolytes. You have to have positives and negatives. If we were to think about the electrons of a metal on just its normal set, think about the hallway during class change. Some people are going towards the commons, some people are going towards the other end, some people are stopped. Some people are walking really slowly. Some people are going really quickly. Some people are making out, which is really gross. But you get what I'm going. It's kind of chaotic out there. People are, if every one of those students was an electron in a metal, they have the ability to go whichever direction they want to go and the speed that they want to go in. If we were to stop that, though, if I were to pass an electric current and all of those students, instead of being chaotic and moving in multiple ways, everybody would be like an ROTC. We would all be in one direction, marching the same way, same speed, and across. And that would allow us to carry the electric current from one end of the sample to the other. So metals have mobile valence electrons, referred to as the sea of electrons because of that motion. Those mobile valence electrons allow the metal to be malleable and ductile because they will not break when pressure is applied. They will simply adjust and move out of the way. They can be smushed into empty spaces. And metals are great at conducting electricity because we can take all of those flowing electrons and they can move in one direction to carry that electric current across the sample. All right. Last but not least are alloys. And I do want you to at least be familiar with what an alloy is. An alloy is a mixture of two or more elements, one of which is a metal. Most of the time, they're mostly metal, but not always. An alloy is a mixture of two or more metals. The reason that alloys exist is because the creation of the alloy gives it superior properties than the metals that make it up. It's kind of like getting the best of both worlds. This metal is good at this, and this element is good at this. So if we mix these, they can be extra good at something. Probably the best example, and definitely not the only example, but the one that you'll see the most often is steel. Steel is an alloy. It is made of iron, chromium, carbon, and nickel. Steel is used in building cars and buildings and bridges and infrastructure. And I mean, there's so many uses for steel. Not just stainless steel like we cook with or silverware, but as far as like the infrastructure of our country or the world in general, steel is a integral part of that. It used to be iron, but as steel industries have grown, they're able to create a superior product. Iron rusts really easily. So if you have a bridge made of iron, you can expect to have to replace that a lot sooner than if you have a bridge made of steel. Adding carbon, carbon is the strongest thing there is. Think about a diamond. Diamond is just pure carbon. If you add carbon to this, we increase the strength. So now we're stronger than iron and we won't rust because of our chromium and nickel. And that's it. That's chapter 7, section 3. We're done with chapter 7. Yeah, yes.